Marcel Mansfeld. I will remind you of the house rules, please. Please keep your mics muted and your camera off until the speakers invite you to take the floor. When the floor is yours, please avoid overt political statements, offensive language, and commercial pitches. If you do have questions, please put them into the chat here on the platform. Speakers will take them from there, and there will also be a short Q&A at the end of the session. This session is recorded, and the recording will be available on the platform later. And that's all for me. Over to you, Csaba.
Thank you and good morning, everyone. In this presentation, Marcel and me will be briefly describing some of the insights from our experiments with building powerful and high-quality machine translation models on computer infrastructures, which are unfortunately not normally available for our production workflows. So bit of a background about the eTranslation service itself. As you might already know, this is the European Commission's machine translation service. It is now only one of many NLP services in the Commission, but it's still an important one. We are providing secure access to neural machine translation systems for many language pairs. And to train the systems, we use the internal high-quality translation database, the Euramis translation memories. And we have quite a substantial workload. So we continuously trying to improve the quality of the service, but unfortunately it has a price, because for high quality machine translation services, you need a kind of a trade-off and you need to find the right balance between the use of the available resources and the best possible performance of the models, because nowadays there is a clear tendency to go bigger and bigger, because the assumption is that with increasing model sizes, we get better performance at the same time. But these big models definitely need substantial computational infrastructure to train, and sometimes they just can be inefficient in the production workflows. So our plan with this project was to try to use high performance computing resources to train deep and powerful machine translation models to get the highest quality that we can, and just try to resolve this resource performance dilemma with an approach that is called knowledge distillation. Knowledge distillation is basically a well-known method to transfer the knowledge of a complex and highly capable teacher model to a much smaller, but faster and more efficient student model, in a way that we first train the complex teacher model to actually get the most out of the data at our disposal. And then we try to use the teacher's output to help the student's training in some way, where the student's aim is basically to mimic the teacher as close as possible. And surprisingly, this way, the performance of the student gets better than if the student only uses the original data set. So that's knowledge distillation in a nutshell. So to summarize the objectives of our project in using these high performance computing infrastructures, we wanted to explore the potential of deeper models. So how far we can get actually by increasing the model sizes, and how far we can improve the quality of machine translation with these models. We try to investigate the scalability of trainings in the HPC environment. So how many trainings we can run in parallel, how fast we can finish the training of one or the other model. And definitely we wanted to create something that would benefit in the end the eTranslation service in general, by kind of setting up some stable workflow that we can transfer to production. With these added functionalities that we wanted to preserve, I mean something like being able to restore formatting information on the text input, or support the ability to copy marked up parts of the source side to the target unchanged. So these kind of functionalities. So we had basically a pretty straightforward workflow. We had to train the strong teacher models, perhaps ensembles, in the sense that in this setup we train several models for the same language pair, and then we use the output, the combined output of all of the models to produce the final output of the ensemble. And the second step was to decode the training data with the teacher models in preparation for the student training in the knowledge distillation approach. And at the same time, we had to find some kind of an optimal student architecture and select it to actually train the student models on the teacher decoded dataset. Now we had limited access this time to the HPC resources, so we only did the first step on the HPC infrastructure. For the rest, we used our local cloud environment. So a few words about the teacher models. They are basically common configurations, the so-called big transformer machine translation models. And compared to our baseline production models, you can see that they are significantly larger and more complex, like 10 times. But with the more powerful compute infrastructure, we could achieve the same training time for these big models as the average training time of the production model in our local environment. If you build definitely teacher ensembles, then we have to multiply the resources needed by the number of models that we use in this in one or the other ensemble. But in the end, definitely we get significantly better quality, and 10% in machine translation terms is really a huge increase. Definitely there are issues. If we have requirements for high speed and low latency in production environments, then we might have a problem with deploying these models, and also the training can be sometimes pretty expensive. So for the student models, there are practically an unlimited set of options here, and we have to find some kind of an optimal architecture, a trade-off between quality and model quality and efficiency. And because of the limited resources, we run this set of experiments to find the optimal architecture on only one language pair. And once we finalized our student model setup or configuration, then we applied this setup for the other language pairs as well. But in the end, we ended up with something which was 10 times more compact than the teacher model. This specific setup trains a bit slower than our current production models, but is much faster and produces comparable or even slightly better results during translation. We also experimented with multilingual models where we observed only a slight drop in quality, but they are definitely more efficient in training and inference, because in this case you use just one model to serve several language pairs at the same time. In the trainings, in the first stage, we focused on 6 language pairs, all to English as a common target language, and from 2 language families to facilitate the experiments with the multilingual setups. And for the data, as I mentioned at the beginning, we used the Euramis database, which in machine translation terms can be considered really a high quality and high resource parallel database, where the number of segments across the language pairs is pretty high, and but more or less comparable. So from 20 something million to 33 million segment pairs. So how much power did we have at our disposal in actual fact in this HPC environment for these trainings then? So we measured the average speed of the teacher models trainings in our local environment and in the HPC environment in the number of words, 1,000 words per second, by the number of GPUs that we used for a model training. And as you can see, the difference is really substantial. But unfortunately, you need this power to actually efficiently train these more complex models. So let's see how good, in actual fact, these models ended up after the trainings. We run some automatic evaluation on our internal test data sets. And as you can see, clearly the deep complex models compared to the baseline production models are definitely significantly better. But even the student models are comparable or slightly better. And the multilingual setups also yield acceptable quality, obviously accompanied by a lot more favorable deployment conditions. But we've also been looking into the output of the big models in some details manually. And then, so at this point, I will pass the microphone to Marcel to speak about human evaluation and illustrate some of the findings there.
Yes, indeed. Thank you, Csaba, and good morning from me as well. So what I received for review in February of this year was a sample of around 500 segments translated from German into English. And for each of these 500 source sentences, I got 3 translations, as you can see in the on the screen. And the first translation was produced by the normal machine translation engine that was used in production at that time. That's the production model in the second column. The second translation came from the new machine translation model that was trained by the Maluxina supercomputer. That's the HPC model. And finally, the final translation was created by a colleague from the English language department of DG Translation. That's the human reference there. And it's important to note that the MT models had obviously not been trained with these sentences before, nor did the human translator work with a machine-based translation when he or she translated them. So what I saw most frequently in my analysis of these different translations were cases where the wording and or the syntax of the Maluxina sentences were better than the normal machine translation. In this first example concerning access to health services, we have 4 superlative adjectives in the German source sentence. And as you can see in red font in the second column, the regular machine translation failed to reproduce 2 superlatives and also picked 2 adjectives that are not ideal here. The adjective simple doesn't go so well with access here. And the word next is at least misleading because it fails to convey this idea of physical proximity, which is important. Maluxina, on the other hand, so the HPC model, got it all right here and predicted exactly how the human translator would have put it, or then actually put it when he translated it. Yes, now the second example, here the regular machine translation in the second column failed to recognize the internet address gemeinsam4.eu and got confused about it. And Maluxina, on the other hand, had apparently captured that address before, so that it could even provide the equivalent English internet address here that I'm sure the human translator had to research and to find out that there was this internet address actually had to be translated here. Plus, Maluxina also capitalized 2 terms here. That's the contributing users and the contributing organizations. And so did the human translator. And throughout the whole sample, I actually found quite a few cases where Maluxina correctly capitalized terms, for example, names of organizations, committees, or legal acts, that the regular machine translation did not capitalize. So quite nice improvement here as well. Yeah, the next category that I wanted to show you concerns technical terms. This sentence here contains 2 technical terms in the beginning and in the end that appear in the IATE terminology database. And both Meloxina and the human translator came up with the terms portable batteries and battery chemistry from Yate, while the regular machine translation simply translated them word by word. So that's very nice again. And in the end, I'd like to show you an example that is particularly interesting because the translation of the Meloxina model is not only better than the regular machine translation, but also better than the human translation here, curiously. In this sentence, the regular machine translation mistranslated the word besuchen, which is ambivalent in German a bit, by attend, which is wrong here because the member obviously will not attend the school as a pupil, but simply goes to visit it for a day. The term pupils is also more appropriate here than the word students, because we're obviously talking about younger pupils at a school instead of older. And at the end of the sentence, we have an example where both machine translations are correct, while the human because the human translation falsely suggests here that the teacher was selected from a group of candidates as well, which is obviously not the case according to the German original sentence. So yes, to sum up my impressions, in general, I think these examples and also the big picture that I saw clearly show that the Meloxina model offers very promising improvements for us translators. And no pressure, Csaba, but we look forward to seeing them implemented in production as soon as possible.
Yeah, so yeah, definitely. So if they are so good, I mean, these big three teacher models are so impressive, then we can ask how we can actually leverage these big models in production. So currently, what we have is a kind of a hybrid system. We could say components composed of stochastic and symbolic modules, and which is a bit complicated and slow at the same time. It's a pipeline approach of multiple components that actually do a lot of steps and filter or simplify the data before it even gets to the actual translation model. And well, one could perhaps even assume that these external modules can even hide or obfuscate potential useful information that the model would be able to utilize during the translation. So you might think about a kind of an alternative no pipeline strategy, because if you just plug in the big model and then replace the small model with the big model itself, then it might not be in the best interest of an efficient machine translation service to add even more overhead to this pipeline. But we've seen that these deep models are already very capable, so why not try and let them do everything? So if we illustrate this, what we have like kind of a pre-processing steps, it's just a simplified setup. It's not the whole. We have specific modules responsible for the transformation of the input into something more favorable to the model. Who knows? And then on the target side, everything is more or less reversed to get the ideal surface form. But what we can do is basically just replace it with the whole pipeline with the single big translation model, and which just works with the raw input and produces the final output without any intermediate steps. And this way, we don't really lose efficiency as far as the whole pipeline is concerned. So that's definitely is a possibility. So how are we planning to improve eTranslation as a result of these HPC projects? As it turns out, both types of products, like the deep teacher models and the fast student models of our HPC adventures, can be actually utilized in service. If we have a deployment environment with less demanding conditions, then we can use these teacher models directly, because the speed is still acceptable. The resource need is not that much prohibitive, and then as we've seen, the quality is clearly much higher. On the other hand, if some quality can be sacrificed for efficiency, or efficiency is the primary, then we can use the student models as well. So to conclude, what are the lessons that we learned from these experiments and from this project? Well, we can say that if we have close to unlimited resources, we can still go a long way with the task-specific AI models. So in this case, models specifically developed for machine translation, for the task of machine translation, is nothing else. So they are not general models, even if they are kind of deeper than the standard or normal machine translation models. And it's true that we might have to pay a little bit more than usual, but it's still possible to keep the costs manageable. And we can assure you that the open sourcing of the models are already in progress, and we are also planning to scale up to all supported language pairs in the near future. And with that, I think I finish here, and our special thanks go to the providers of the computer infrastructure, and also to the audience for their kind attention. Thank you.
Thank you very much, Csaba and Marcel, both for your wonderful presentation. Now is the time for our colleagues in the audience to put questions into the chat. Before the first one arrives, I have a couple, if I may. Wait a second. I was taking notes here very painstakingly. So one of them, that would be about the data. You were saying that you were using Euramis data, which is high quality, high resource, but it's still a relatively homogeneous amount of data, right? What we're getting from Euramis. And as far as I know, that there is some amount of non-Euramis data also being used for the training.
Yeah, I left this part out of this presentation because of time constraints. So these were not so these models are actually specifically for the EU formal language. But we have other types of models, and we have trained actually other models in this supercomputer environment. The findings are more or less similar, so we get the same quality jump, but it's even more painstaking. The trainings are even more painstaking because there we have a lot more data. So there we are in the hundreds of millions of segments, in the range of hundreds of millions of segments. So yeah, so we have those as well. I haven't touched upon that part of the project in this presentation, but true, that's true.
Thank
so
you.
That's just only part of the story here.
And while still waiting, so there's time for one more of mine. You said that essentially the costs are rising with the amount of compute that's needed, etc. Is there a point where you can see that machine translation would become more expensive than human translation? Or is it about the scale of how we
no,
use it?
no, I'm still, I think we are still very far from that magnitude. Yeah. So, and then there are means to actually rationalize these training costs, even in this setup that we've been working with. So we are still very far from that. I don't know whether it's good news or bad news, but I would say that.
I expect that it would also scale very well with the amount of translation that we do with it afterwards. So
yeah, obviously.
Okay.
Yes.
Well, fair enough. About the increased compute, it does look like it's really helping a lot. Can you give a scale of Melusina compared to the supercomputers used by other large machine translation services, things like DeepL or Bing Translate, etc.? Can you?
I don't have reliable information from those players at all. I don't know. Might be using something similar magnitude, but I'm not sure. I don't know. I mean, definitely to train a single machine translation model, the resource that you need, or the computer infrastructure that you need, is already available widely in the cloud and served by many cloud providers, but it's not cheap at all. So, and then if you need to do large scale trainings for models for many language pairs, then this would be really substantial cost. So it's not really um, uh, an unusual computer infrastructure that you need for these models, but it could be very costly on a large scale.
Understood. We have a first question from one of the audience members, if you can see it in the chat, from Luz M. Why haven't you trained from Spanish and Italian into English too? And again, what is a teacher model? Thank you. It's going to be hard.
Yeah, we will be training models from Spanish and Italian as well. We have, so in this access to this environment, we had a limited time and a number of node hours actually, so limited resource, and then we had to restrict the number of language pairs that we were able to work with. So. And then the second part of the question, we call the deep model, the more complex model, the teacher model, because we use the output of this model to train the smaller so-called student model. So that's why the setup is called the teacher-student kind of setup or something. So we transfer the knowledge from the big model to a smaller model, and then in this setup, the big model is called the teacher model because we use the output from this model to actually teach the student model to behave the right way. And then
okay, we are getting more questions now. So first was Alex Korniakov. What's the range of blur scores for different European language groups? You have it
it's
by
pretty,
heart?
it definitely depends on the test set, but it's similar, and the more challenging languages are in a bit lower range, I would say. So that's in very general terms, but it can be anything. So it depending on the test set, it can be anything. So for this specific experiment, we get very high blur scores in the range of 50 or even 60, but for other test sets and for other language directions, we would remain in between 30 and 40, but it doesn't say anything out of context. But in general, we still have kind of more challenging language groups where the scores are a bit lower, but not that much that it was, I don't know, 10 years ago or something.
Next one would be Stephen Fiocco. How much of what we get in eTranslation is already a direct result of these training models you've just discussed? My language pair is Italian into English for context.
It's not yet.
Not yet live.
Not yet live. No.
So
we still need 1 or 2 months, or perhaps, I don't know.
That would be my second question. If it's not live, when is it coming? So soon.
Yeah, next year. I hope next year. Yeah, we'll be able
Right.
to serve some of these models in production.
Tizirine Izzy, how representative are the examples you quoted, knowing that blurred benchmark is reported to be flawed? That's a good one.
Yeah. I don't know if the slides are going public, but I have an appendix where I have more detailed tables, and there I reported other scores as well. And then this, so the difference is so big that the score doesn't really matter here. So definitely the more complex models are just so much better than the score is just. So this chart that I displayed was just for illustration, but I could have used any other score, and the human evaluation confirmed the results as well. So
yeah. I saw that 2-3 years ago we would still be talking about their scores mostly, which I don't think were the best representation of quality. I think that Blur does a little better there. I know there is some talk of Meteor. I guess you may have been doing that too.
Yeah. But now we can also use kind of language model based or embedding based scores, which try to capture more the meaning of the sentence rather than kind of edit distance type of differences. But in this case, we get the same results there as well. So we tested and measured using those cores as well, so embedding based cores as well, and then that's the same result.
Okay.
That
Well,
we got.
Csaba and Marcel, thank you very much for your presentation and for answering all the questions. Thank you to the audience for having those questions in the first place. I wish you a pleasant rest of the last day of DEF this year, and I will see you all at the plenary.
Thank you and bye.
Thank you. Bye bye.